Good morning, everybody. Let us start with module number 5, which talks about formulation of impedance bus matrix, where we will be dealing with Z-bus formulation using step-by-step building algorithm, where we deal in detail when a branch is added to the partial network, which is case 1, and when a link is added to the partial network, which is case 2. So first we should understand what is this Z-bus building algorithm and what are we up to in this content. So earlier in module 1 we have seen Y-bus, building Y-bus by the method of inspection and singular transformation, where whenever a power system network is given to us which has buses and transmission lines interconnected, we try to build the admittance bus matrix by taking into account the admittance of all the transmission lines in the interconnected network. If we write them in the matrix form, we get bus admittance matrix. Similarly, here for any given power system network, we try to build bus impedance matrix. So there are two approaches basically for this. The first approach for building bus impedance matrix would be uh, to obtain the bus admittance matrix, which is Y bus, and then take the inverse of that matrix to get Z bus. But that approach would be very tedious because as the size of the network increases, the Z bus would be of higher size, maybe of the order greater than 6 cross 6. At that point of time, finding the inverse of the matrix again becomes a tedious task. So in order to avoid that problem, here we go for step-by-step building approach, which is the second approach. So here we'll be building the impedance matrix for any given power system network containing buses and transmission lines. So now we'll talk about the algorithm, then we will go into the mathematical modeling. So the first point, whenever impedance ZB of the branch is added from new bus to reference bus, dimension of Z bus goes up by 1, and this is type 1 modification. So what we literally do here is, whenever a simple power system network is given to us where we have number of buses which are interconnected by transmission lines, we start to build the same step by step from scratch. That is, first we are going to consider two buses out of the network, any two buses and a transmission line in between. So we are going to consider one of those buses as reference bus and the second bus as new bus. One bus will be treated as reference, second bus will be treated as new bus, and the transmission line which is interconnecting them will have an impedance ZB. ZB refers to branch impedance. So in this event, the dimension of the Z-bus matrix increases by 1, because so far we don't have any network. Now we are bringing in two buses and a transmission line in between. So we will be writing the Z-bus, which contains one element, one transmission line is there. So the Z-bus matrix will have one single element. So before this it was 0 cross 0. Now since we have added one element, the size becomes 1 cross 1. So dimension of the Z-bus has gone up by 1. So that is called as type 1 modification. Whenever we try to add a branch, a transmission line branch having impedance ZB between a new bus and reference bus, it is called type 1 modification. Next, let us go to the second point. Whenever ZB is added from new bus to old bus, dimension of Z bus goes up by 1. This is type 2 modification. So let us come back to the example that we were talking about. We had taken two buses and one transmission line. We had bus number 1, bus number 2, and a transmission line interconnecting them. We had taken bus 1 as reference. We had considered bus 2 as new bus. Now into that network, now we are bringing in another bus and another transmission line which is interconnecting bus number 2 and this new bus. So the original network containing many number of buses and transmission line is being rebuilt step by step. So in the first step, we had taken bus 1, bus 2 and one transmission line in between. Now in the second step, we are introducing bus number 3 and a transmission line interconnecting bus number 3 and bus number 2. So at this um, point of time, we are going to treat bus 3 as the new bus that is being introduced into the network, and bus 2 was already there earlier. It was already introduced in the previous step, so we are going to treat that as old bus, and the transmission line interconnecting this new bus and old bus will have some finite impedance. Even in this event, the dimension of Z bus goes up by 1. So if we write Z bus matrix now, its size will be 2 cross 2. In the previous step it was 1 cross 1, now it will be 2 cross 2. So this is called as type 2 modification. That is, whenever ZB is added between a new bus and an old bus, it is called type 2 modification. So as of now in our network we have bus 1, bus 2 and bus 3. Next we'll try to understand point number 3. Whenever ZB is added between an old bus and reference, dimension of Z bus does not change. It is type 3 modification. So in our example that we have considered, let us consider that we are interconnecting bus 3 and bus 1 with a transmission line having impedance ZB. So bus 3 was already introduced in the previous step. So you can consider that as old bus, and bus 1 was assumed to be reference in the step 1 itself. So it is as good as adding a transmission line between an old bus and reference. This will be called as type 3 modification. In this event, dimension of Z bus will not change. However, contents of the matrix will get modified. Elements of the matrix will get modified. How it will get modified, we'll understand that in the algorithm. Here we are just talking about the size. So size remains 2 cross 2. Then let us assume there is bus number 4. In this particular instant, let us assume bus number 4 is introduced and we are interconnecting bus number 3 and bus number 4 with another transmission line. Since bus number 3 was already there in the network, we treat that as old bus. Bus number 4 is newly introduced. So when we are adding a transmission line branch between bus 3 and bus 4, it is as good as adding between old bus and new bus. So type 2 modification has been repeated. Then finally, let us go to point number 4. Whenever ZB is added between two old buses, dimension of Z bus does not change. And this refers to type 4 modification. For example, at this particular stage, if we are including a transmission line between bus 2 and bus 4, bus 2 was already existing, bus 4 was also existing. So between those two existing buses, if we happen to add a transmission line with branch impedance ZB, that event is called as type 4 modification. Again, here also dimension of the Z bus does not change. Whatever may be the dimension of Z bus in the previous step, same dimension will be there here also. However, only the contents are going to change. Now let us talk about the notations we are going to use here. I and J are notations for old bus, K is the notation for new bus, R is the notation for reference bus, ZB is the notation for branch impedance included in every step. Now let us go to mathematical modeling. So far we were just talking about the size of the Z bus, how it changes in case of every modification. Now let us see how the contents will be changing, or how the contents can be content or elements of the matrix should be written. So here, modeling of Z bus type 1 modification. So whenever we say addition of a branch to the partial network, it refers to type 1 and type 2 modification. So let us start with modeling of type 1 modification. So if you have a look at this, we have a passive linear n bus power system network represented by a block. So roughly, the block must contain a transmission network containing transmission lines, interconnected transmission lines and buses. So if we try to bring out the terminals of the buses outside this block, it looks like this. Say 1 N, I, J, K and R, where 1 is the first bus, N is the last bus, I and J are some intermediate buses, K is some other intermediate bus and R is reference bus. So as per the definition of type 1, we are supposed to include branch impedance between a new bus and reference. So the notations that we have considered are I and J old, K is new, R is reference. So here I and J are old, K is new and R is reference. So we are adding ZB, as you can see here, between K and R, which is between new and reference. So the potential difference between K and R is Vk, current flowing through ZB is Ik. So from the given network, if we try to write the expression for potential difference, Vk will be equal to Zb into Ik. Now, if we try to write it in matrix form, we will mention Zki is equal to Zik is equal to 0, where I can take the value from 1 to n except the value of k, and reference bus will not be taken into consideration here, and Zkk is equal to Zb. That means the diagonal element Zkk, the last diagonal element is equal to Zb. However, all other row elements and column elements with respect to this new element are zeros. So we can see the same representation over here. We assume that already some old bus was existing, and then type 1 modification is carried out. So we have k over here, which is the new element that is being introduced. So Zik and Zki are zeros. That is, all these elements are zeros. Only the diagonal element Zkk is equal to Zb exists. So this finishes the modeling of type 1 modification. Next we'll move on to type 2 modification. So in type 2 modification, again we take the same passive linear n-bus network. Now we are adding ZB between K and J. K refers to new bus, J refers to old bus. And we know by definition it is between new and old. ZB is added between new and old bus. So from the network, we try to write the expression for Vk. See, Vk is nothing but potential difference between K and R. Ik is current flowing through the branch. We have Ij, which is current entering bus J or injected in bus J, and the current that is entering into the partial network from this particular junction is Ij plus Ik. So if we try to write the expression for Vk, it will be Zbik plus Zj1I1 plus Zj2I2, and some intermediate term that is current injected at bus J will be Zjj into Ij plus Ik. This follows till the last term Zjn into In. So we have written Vk is equal to Zb Ik plus Vj. In place of Vj, we are writing this entire expression, which is nothing but giving us drop across each of the elements. Let us rearrange this expression, and we'll see to that we arrange them so that it will be a coefficient of I1, I2 up to the last one. However, coefficient of Ik will be Zjj plus Zb. Then if we try to write it in matrix form, we have Z bus new is equal to Z bus old. We will have some column elements and row elements Z1j, Z2j, Znj, and here Zj1, Zj2 up to Zjn, and the last diagonal element will be Zjj plus Zb. So the mathematical model will be Zki is equal to Zji, where I varies from 1 to total number of buses. It cannot take the value of k, and Zkk, the diagonal element will be Zjj plus Zb, where J represents old bus. Next, we'll move on to type 3 modification, where a branch impedance is added between old and reference. Dimension of Z bus will not change. This can also be considered as addition of a link to the partial network. So consider the passive linear n-bus network here. So we can observe that ZB is being added between J and R. J is old bus, R is reference. So we don't have to represent this separately. In the type 2 representation itself, it can be done. So let us see how it will be done. So coming to the type 2 representation here, if we just short circuit K and R, we get this type 3 representation. If we short circuit K and R, our VK will become 0. So you'll be left out with a branch impedance added between J and R, and K will not exist. So you can see ZB is now between J and R, VK has been 0. So what we do here is we take the expression that we have got in the earlier step. Vk is equal to zj1i1 plus zj2i2 plus up to zjjij, zjnin plus zjj plus zb into ik, and we substitute vk is equal to 0 for this type 3 modification, and then we rearrange and try to get the expression for ik, which is given by minus 1 over zjj plus zb followed by multiplied by zj1i1 plus zj2i2 up to the last term. Now we try to write the expression for voltage at bus I in general: zi1i1, zi2i2, zin plus zij ik. Now in this expression we substitute for ik from equation 1. So once that is done, we try to rearrange them, group it in terms of coefficients of I1, I2 and In. So we have Zi1 minus 1 over Zjj Zb multiplied by Zij Zj1 into I1, and similarly second term up to the last term, and we try to write it in matrix form. So when you write it in matrix form, the first terms here, say Zi1, Zi2, Zin and all, represents old bus elements, and this represents the intermediate term. So we can write this as Z bus new is equal to Z bus old minus 1 over Zjj plus Zb into a column matrix and a row matrix. A column matrix Z1j up to Znj, and row matrix Zj1 up to Zjn. So here we have written the expression for Z bus. The previous expression, what we can see here, if we write it in matrix form, we have a voltage matrix, column matrix on the left side, and on the right side we have a Z bus matrix, and then current column matrix I1, I2 up to In, and then we just try to represent Ik at the end. So Z1j, Z2j up to Znj, Zj1, Zj2 up to Zjn over here, and Zjj plus Zb will be there as the diagonal element. Next we'll move on to type 4 modification, where we add ZB between two old buses. So I is on one old bus, J is another old bus, same partial linear n bus network. ZB is included between this, and let current IK flow through ZB. II is current injected at bus I, IJ is current injected at bus J. So the current that is flowing out of this node is II plus IK, while the current flowing out of this particular node, what I am representing, is IJ minus IK. Now we repeat writing the expression for Vi for this network. It will be Zi1i1 plus Zi2i2 plus Zii into Ii plus Ik in the ith element plus Zij into Ij minus Ik up to the last element. And then we also write the expression for Vj similarly. Then voltage of buses I and J are related as follows. So from this network we can observe that Vj minus Vi is Zb into Ik, or Vj is equal to Zb Ik plus Vi. We have the expression for Vj and Vi over here. We have to just substitute the same in expression 1. So if we substitute the same in expression 1, we get this Zj1i1 plus Zj2i2 plus so and so Zji Ii plus Ik, Zjj Ij minus Ik up to the last term. On the RHS we have Zb Ik plus terms corresponding to Vi, which is Zi1i1 plus Zi2i2 up to Zii into Ii plus Ik, Zij into Ij minus Ik plus Zin into In. Next we try to rearrange the same. If we rearrange the same, I try to bring all the terms on the LHS onto the RHS. So I have 0 is equal to Zi1 minus Zj1 into I1, Zii minus Zji into Ii, followed by the remaining terms as we can see here. Then the mathematical model would be Z bus new is, see all the first terms here also represent old bus elements. Second one represents a combination. So Z bus new will be Z bus old minus 1 over ZB plus ZII plus ZJJ minus 2ZIJ multiplied by a column matrix and a row matrix having Z1I minus Z1J up to the nth term, ZI1 minus ZJ1 up to the nth term in this row matrix. So if you just write it in the standard format, we have voltage matrix on the left side, Z bus matrix, and then current matrix on the right side. So this finishes the mathematical model for type 4 modification. So this finishes the content of module 5 under Z bus formulation mathematical modeling. In the next session, let us see sample problems.